space as a building block for adding new systems, new capabilities, and using this advanced technology of solar electric propulsion that I'll describe for you later. In addition, as we look at sending huge payloads to Mars, which is what we're going to need if we start sending humans to Mars, electric propulsion is a key tool. We can deliver much more mass, much more efficiently than we can with chemical propulsion. And you'll get that in a little bit later in the talk. So again, these are all the key building blocks of where eventually we're going with human exploration. So the Asteroid Redirect Robotic Mission requires three things. It requires us to find the targets and characterize the targets. It requires us then to actually go rendezvous and redirect the target, and then bring it back and allow the crew to explore it. We use ground-based and Earth-orbiting observatories to identify asteroids. As a matter of fact, we've had systems on the ground and in space that have been looking for hazardous asteroids for almost a decade now. And hazardous asteroids are things that are half a kilometer in diameter or so, or bigger. Earth killers are kilometer class, the civilization ending or multi-kilometer size. We've decided that now we need to look for asteroids as small as 140 meters. And so we've increased the capability to do those observations with better and better ground-based observatories. What we realized is that we could use those same observatories to look for even smaller asteroids. Something like Chelyabinsk, that was a 17-meter or so asteroid. It's hard to find these small objects because they're moving fast and they're really dark. But we've got now these kind of capabilities to identify these targets. The redirect mission I'll describe in much more detail, and describe in much more detail about the crew exploration phase. So let's talk a little bit about asteroid targets, things that we care about. What these are the targets associated, these are big asteroids. These are asteroids in the hundreds of meter class. And there are certain parameters that are really important to us. First of all, we care about the type. That's very interesting to us, particularly if eventually we want to do science or resource utilization. Those tend to be the C-type, the carbonaceous chondrite types. The stony types are much more common, or at least we have seen many more of them. And those are not so interesting from those point of view. But they're still valid targets for us. Care about the size to some extent. We care a lot about the rotation rate. If they're spinning too fast, we can't land on them safely. We can't operate on them for a period of time. We also care a lot about V infinity. V infinity is the velocity that the asteroid is coming by the Earth at. If it's coming too fast, it takes too much energy to get there to rendezvous with it. So the lower the V infinity, the better the target. How close it is to the Earth, or to the Sun, I should say, perihelion distance is also very important to us. And the magnitude, the absolute magnitude, is the brightness. It gives us a sense of the size. We've picked, for this mission, a target we call 2008 EV5. And I'll describe that one a little bit more for you. But it's got all the right properties. It's kind of the Goldilocks asteroid. Good spin rate, very low infinity, and close to the, and basically very much the same orbit as the Earth. Yeah, you see here on the screen two pictures. One is Itokawa, which is the asteroid Hayabusa 1 went to. You can see the quality of this. This is the best photographed asteroid that we have ever seen. And you can see on it all these bumps. Those are boulders. Those are things that we could go and pick up. And I'll describe that nature of that mission. Everything we know about the target we're actually going to is that picture of 2008 EV5. That's a radar image, Earth-based radar. And that's about all we know about it. But we've done a lot to understand that body. Here is the shape model. This is what it looks like. It's about 300 meters mean diameter. It's a fairly nice shaped object. But we're going to go try to find a boulder on this surface. We don't know for sure if there are boulders there. And I'll talk about that problem in a minute. But why an asteroid? Why should we go to an asteroid, and why should we bring it back? Well, these are the main reasons. First of all, I'm going to describe to you a technology in solar electric propulsion that's going to need to be tested. And we want to test it by moving a very large mass around the solar system. And that's what we're going to do when we're going to need when we send humans and want to transport humans and human support systems out to Mars. So we need this kind of capability. We need to demonstrate it. We like this, I already mentioned the carbonaceous chondrite asteroid. That's the type we'd like to go to. Has the greatest science and the greatest resource utilization opportunity. And then we want to demonstrate the ability to actually land on a body. We're not going to just fly around it, we're actually going to land. We're going to go down onto the surface and grab an asteroid and bring it back, pick it up. Then we're going to do with the crew this integrated set of operations. The crew actually will rendezvous and dock with the robotic machine in deep space. That's never been done before. Then the crew will egress and go and hand over hand across this spacecraft out to the asteroid and sample it. While we're out there, we're also able to do something which is really unique, which is a planetary defense demonstration. I'll describe that for you in a second. And of course, a big part of the reason I'm here for I like to call it the Off-World Mining Conference, the Off-Earth Mining Conference, is resource utilization. And I'll talk about that a little bit later on. So the asteroid is really an ideal target for us. So here are two missions. When I was first offered the job of ARM, there was really only one mission. It was the idea of rendezvousing with a 1,000-ton vehicle, a 1,000-ton asteroid. Free flying, something that might be 10 meters in diameter. It's a big, big body. We were going to capture it in a bag. Why a bag, you ask? Well, we know almost nothing about the structure of asteroids. We don't know what holds them together. The gravity is so weak, it can't only be gravity. There's other forces involved. But they may just be very loosely held together. So the idea of a bag was the right answer. You could capture it in a bag, close it, and I'll describe a little bit more how this design works. And that's the way to do that kind of a capture system. As I mentioned earlier, the key here is solar electric propulsion. This is a capability that can deliver huge masses, move huge masses over time. Again, I'll describe that in some detail. After we'd been working on this for a while, we started to realize that we're not finding a lot of targets. We're not finding a lot of interesting asteroids of just the right size. So we went back and looked at the concept that came out when we first came up with this whole mission. What about going to a bigger asteroid and picking up a smaller boulder, something that maybe that's 20 tons or maybe even less? So this gained some traction and started to have some advantages. And the biggest advantage was, first of all, we can go to the type of asteroid we want to go to, a carbonaceous chondrite asteroid, something that we think maybe have hydrated minerals. This is something that's very interesting to the resource utilization community and to the science community. So big advantage there. Another thing that this offered, it offers the opportunity to gain experience in actually landing on a microgravity body in deep space, when we're going to have to be doing highly autonomous operations. So this is going to push the state of the art in a number of directions, but it's also a much more complicated mission. Believe it or not, rendezvousing with and capturing a 1,000-ton asteroid in deep space is an easier job than landing and trying to pick up a boulder. And I think you'll get a sense of that as I talk more. So, this is what the machines look like that would be needed to execute this mission. These are very large spacecraft. On the left, you see, or on your left, you see the capture system associated with grabbing a whole asteroid. And this involves very large inflatable structures. On the right side, you see the large robotic arms associated with actually being able to land on the surface and grab a boulder. The thing that makes this thing really big is it requires 10 tons of propellant. 10 tons of xenon are required to drive this system. The power system is 55 kilowatt electric solar arrays driving 40 kilowatts into this electric propulsion system. By comparison, the Dawn spacecraft, which is currently the most successful electric propulsion system in deep space, is 2.5 kilowatts, not 40, 2.5. and has a solar array that puts out about 10 kilowatts. So we're talking about significant advancement in the capabilities. And its propulsion system carried half a ton, not 10 tons. So I want to just explain to you these two concepts a little bit more. So we call them option A and option B, very creative names. But the capture the whole asteroid part involved an inflatable system. So we built, I've worked with soft goods, this is what we call them soft goods. I've worked, the airbags that we used for landing Pathfinder and Spirit Opportunity were things that I was responsible for. And inflatables are very unique, but they don't lend themselves to analysis very well. So you have to build something and test it. And that's what we did. We built a 5th scale test bed at JPL and developed over the course of a year and a half or so a fairly robust design that we thought could do the job. And a design that we could test here on Earth and not have to go fly it in space before we actually use it. And here you see the sequence where the bag basically inflates, it goes around the asteroid. Once the asteroid is captured inside, we close the bag, and we basically have the whole asteroid contained. And from that point of view, we're ready to return, go back to the Earth-Moon system. This is the capture system B. This is the option B. This involves 3 legs. The legs are about 7 meters tall, and they're associated, you'll see this in the animation very nicely, how it will land on those legs, and then we'll use 2 robotic arms, 7-degree of freedom robotic arms, that have a very special end effector on them that allow us to grab the boulder, and then we push ourselves up off the surface. And here, the Goddard Space Flight Center in Maryland, we've built a full-scale test bed, which we can do because the size of the boulders we're talking about here are only about 2 or 3 meters in size. So I mentioned why NASA selected option B. Again, we thought better science potential, resource utilization, new targets, better, and we were going to advance some key technologies that would be useful for human exploration in the Mars system in the long run. So that's our baseline that we've had since about April of this year. So what does the basic mission concept look like? We need to launch on a heavy lift launch vehicle, something what we call the Delta IV Heavy, maybe a Falcon Heavy if that comes online, or the SLS. We've got to launch about 14 tons on a trajectory, an Earth escape trajectory that is on its way out to this asteroid right now, 2008 EV5. We cruised for about 2 years, and during that 2 years, we're burning our solar electric propulsion system continuously in order to rendezvous and sync up perfectly with the asteroid 2008 EV5. Once we're there, we will be doing a variety of things that I'll describe in some detail. We'll spend about 200 plus days in operations around the asteroid. We'll have our boulder in hand, and we'll begin our path back to the Earth-Moon system. On our way back, we have to very precisely target our approach back to the Earth-Moon system, because we need to do a gravity assist around the moon to put us into the orbit that is accessible by the crew, and ultimately to put us into an orbit that is very stable, one in which we can safely leave the spacecraft and the asteroid. At that point, we're ready for the crew to come out, rendezvous with us, and explore the asteroid. The crewed mission I'll describe a little bit more in a minute. So here's what's going on up close during what we call the proximity operation phase. Once we're at the asteroid, once we've rendezvoused with it, we will orbit it and we will map it. We will do what we call characterization. We'll be mapping it very carefully, 1 centimeter class resolution, because we're looking to find boulders on the surface that are the right size, the right characteristics. Now that's a big uncertainty for us. We don't even know for sure 2008 EV5 has boulders. We think it does. Every asteroid we've seen has boulders, but we haven't seen that many. The thing that we really don't know much about is the composition, the strength, the nature of the asteroid, of the boulder itself. Can we pick it up? Can we grab it? How well is it? How tight? How adhered to the surface is it? All those are things we will not know until we actually get there. So after we've done the characterization, we're going to pick a target. We've got to pick a boulder that looks like the right size. And by the way, we don't know the density within a factor of 2. If the asteroid's too massive, we won't be able to bring it back. So we're going to have to make a lot of judgment calls, kind of more or less in real time. Once we've picked our target, though, we also got to make sure it's safe. That we've got a safe place we can land. And again, here, we don't know what's going to happen when we touch down. We don't know the strength of the surface. We have to be prepared for all of that. And we have to do it all autonomously. We'll be probably facing 10, 20-minute one-way light time uncertainty, or one-way light time communications. There's nothing that humans can do, basically, from the surface of the Earth. We have to build it all into the hardware and the software to operate successfully during this phase. And we have to be prepared for every contingency we can imagine, and then some maybe we can't imagine. But once we've grabbed our boulder, and I'll describe that in a second, we then take off from the surface. And once we're up away from the surface, we gain control of the boulder, and now we're prepared to do one more experiment, the planetary defense demonstration. Here's where we basically have now taken the mass of our spacecraft, which was about 14 tons at launch. We've probably burned about 2 tons of propellant, so we're down around 12 tons, and we've added 20 tons to it. And now we're going to stand off from the big asteroid from 2085, go into what we call a halo orbit, basically out in front of the asteroid along its flight path, and with basically a gravity string, we're going to tractor the asteroid in a way to change its velocity a tiny amount, a fraction of a millimeter per second. And with our deep space network, we can measure that. And we'll basically be just demonstrating for the engineering students in the audience, F equals ma. I don't question F equals ma. My challenge, though, is to demonstrate the ability to fly this stable halo orbit for about 60 days, and actually gravity tractor this asteroid a small amount. This is a capability that could be used under certain circumstances if we were faced with a truly hazardous asteroid. 2085 is not hazardous to the Earth. It's never on a trajectory to impact the Earth. But someday we will find one that will be hazardous. And this may be a tool that we could use to deal with that. After we finished our planetary defense demonstration, we're heading back home to the Earth Moon system. Now, picking up the asteroid, that's an interesting problem. We've chosen a particular technology that's very unique. It works well on the end of 2 robotic arms. It's a very unique kind of end effector. Anybody who's worked with robotics, you're used to working with different types of end effectors, claws and finger type manipulators. What this is like a gecko's foot pad. This system we call the microspine was developed based on looking at how geckos walk up walls, up glass surfaces. And we developed a technology that could mimic the gecko, but it wouldn't work on rocks. So we figured out another way to mimic that design that nature has. And we're actually, with thousands of very small little metal spines, we're able to go down, and you'll see this in the animation very nicely, go down and actually grab the surface with its hand and grab hold of the asteroid. And we'll do this in 2 places, and we'll be ready to take off. But here again, we're faced with a big problem. We don't know the nature of the surface. We've got simulants, we've got ideas, we've got great smart scientists telling us everything they know, but they don't know enough to give us great confidence to actually say with 100% certainty we know how to deal with that. So there's a lot of testing and a lot of uncertainty we'll be dealing with here, and we have to be prepared for the fact that maybe the boulder isn't strong enough, and we'll have to let go of the first one and go try another one. So there's a lot of options in our option space. Really? I mean, not a single snicker? Come on. Think about it, the dinosaurs did not have a space program. That's part of why they got wiped out 65 million years ago when a big asteroid hit. So, this is a kind of our joke that, yeah, we have a space program, but we're only just now starting to take seriously the threat that asteroids present. Now, it's a very low probability threat, but it's one that we can manage if we need to. But there's a lot of uncertainty around that. And so ARM is the first down payment on the kind of technologies that can deal with hazardous asteroids. So you see an artist's graphic indicating or showing, the big asteroid or the dinosaur killer 65 million years ago. And then you have the picture from the camera on somebody's car in Chelyabinsk, Russia, showing the explosion of that asteroid as it broke up over that city. So I already talked about this gravity tractor. We call it enhanced because we brought along this extra mass associated with the asteroid, the boulder we brought along. But we can also use another technique that is in our back pocket as another option, which is called ion beam deflection, where we just basically turn our solar electric engines on the asteroid, and by hitting it with billions and billions of xenon particles, we're able to change the velocity that way as well. It's very efficient that way. Again, it's a very gentle push. But if we were really faced with a serious threat, we'd be throwing a lot of things at the asteroid, kinetically, using kinetic energy to try to change its velocity. So this is another possible experiment where we can demonstrate the capability. Now let me talk just for a second about the crew phase. Again, like I said in the beginning, ARM is a key building block for the U.S.'s strategy for human exploration. And by the way, we're engaged with a lot of other countries, or talking with a lot of other countries about their participation in this mission and in the role of human exploration. But here we've got the Orion spacecraft having left Earth orbit, heading to this crew-safe orbit, crew-accessible orbit, where the ARM spacecraft is waiting for it with its boulder, 20-ton, about 3 or 4 meter boulder. And so the crew vehicle has to rendezvous and dock. And this will be the first time that's been done right now, all the rendezvous and docking that's being done is being done at the space station. And there's people on both sides of that interface. This is a case where now it's going to be done between a crewed vehicle and a robotic machine. They're going to be docked with us for about 5 days. During that time, there'll be 2 5-hour EVAs, which the crew will egress their own spacecraft, and the animation will show it to you very nicely. Hand over hand, working their way across the spacecraft, getting to the asteroid itself, sampling it, putting material, bringing back maybe as much as 100 kilograms of asteroid material. We've already done demonstrations of what this crewed mission would look like. We've gone to the Neutral Buoyancy Lab at Johnson Space Center, which is this huge swimming pool, which they have pieces of the space station. They have now built pieces of the ARM spacecraft and actually demonstrated with the current spacesuits that we'd likely use how the crew can actually do these operations. Egressing, working along the robotic vehicle, getting access to the samples on the boulder itself. So we've been proving out the basic systems to make this work over the last couple of years. Now, for all the engineering students in the audience, we're going to talk a little rocket science. What is electric propulsion? Well, it's first a little easier to talk about chemical propulsion. Chemical propulsion is what most of us are used to. It's whether it's internal combustion engines or whether it's LOX hydrogen engines on the space shuttle. But all the energy that comes out of those systems is built into the chemistry of the material. So why we have such huge rockets is because of the amount of mass it takes to lift things off the surface of the Earth. The basic rocket equation. And the efficiency of these systems is dictated by the chemistry of the propellants. The most efficient rocket propellant we have today, hydrogen and oxygen. Now, let's talk electric propulsion. Electric propulsion is a whole different paradigm. The energy that comes from electric propulsion is associated with the power system. It's not associated with the chemistry of the propellant. The propellant is xenon. It's an inert gas. And it's what we wanted was something that had the most massive, atoms we could find, but things that are relatively easy to manage. So the xenon propellant is accelerated through a field, an electric field. And the stronger that electric field, the faster the acceleration. The faster the acceleration, the more efficient the propulsion system. So think of it this way. If you're wanting to move from, let's say Sydney to Melbourne, you're going to want to move your household goods in a moving van. It's going to be slow, but it's going to be efficient. That's what electric propulsion is. It takes years to change velocity, but it changes it by huge amounts. When you're ready to go yourself, you'll jump on an airplane that uses chemical propulsion to get you there. The electric propulsion is what you want when you're moving big masses, long distances. This is an electric propulsion engine. It's called Hall thruster engine. It uses electric and magnetic fields to control the ions that are being accelerated through it. Its exit velocity is 30 kilometers a second. Extremely high ISP. And this system is on the order of 20 times more efficient than chemical propulsion. If you wanted to try to do the ARM mission, in which right now we're using somewhere between 5 and 10 tons of xenon, you would need 20 times that. We're talking 100 to 200 tons of liquid oxygen and liquid hydrogen. That's multiple launches of very large spacecraft. It's not cost effective. This mission is enabled by electric propulsion. And a lot of the stuff that we're doing in the future for human spaceflight is also going to be enabled by electric propulsion. And as I'll mention here in a second when I talk about resource utilization. If you want to move large payloads out, if you want to do mining somewhere, you have material you want to bring back into the Earth-Moon system, EP, electric propulsion, is the way to go. And here's Dawn at Vesta and Ceres. Again, electric propulsion enabled this mission. We basically went to 2 main belt asteroids for basically 500 kilograms of xenon and about 2.5 kilowatts of electric power. It's taken us a few years to do it, but we could not have done this mission, this incredible 2 major asteroid mission, without electric propulsion. And by the way, this is only the second spacecraft ever flown in deep space. The third will be Orion. Now, where does this fit in the big picture, in the schedule? Again, we're looking for targets. We've found the targets we're most interested in right now. We're going to keep looking. We may find an even better target. But we're going to lock down our mission decision, our target decision, maybe a year before launch. And right now we're shooting for launching in December of 2020. So in 2019, we'll lock that down. So the ARM spacecraft, I already told you, will launch in 2020. We'll be back ready for the crewed mission by 2025. And after that, we'd be available for extended missions in which other potential proposals could be made as to how to use the ARM spacecraft and the asteroid that we brought with us. Meanwhile, the crewed mission development is going on. We had a couple years ago, there was a flight test of the capabilities of the Orion spacecraft, very successful, but there were no humans aboard. The next test will be in 2018, where again, there will be no humans aboard, but it will be launched on the large Saturn V class SLS, Space Launch System. But the first time humans will actually be launched and leave Earth orbit on the SLS Orion system probably will be until 2022 or 2023. And they will go to the orbit that the ARM spacecraft will eventually go into. And we'll test out their ability to rendezvous, to operate safely in that space. And we expect the crewed mission to be ready when we get there in around 2025. And we have some flexibility, if some things move a little bit, we can move out downstream in time if we have to. But that's my target today. So now I'd like to share with you a video. And I think we'll see, hopefully it's going to play, and I'm going to tie together all the story that I just told you. You thought landing on Mars was hard. Well, this isn't the 7 minutes of terror, but it's going to be 7 hours of terror, 7 days of terror. This is a very, very challenging mission. And just the sort of thing that me and my team are really excited about doing. So let's talk a little bit about what this conference that I was invited to is focusing on. And this is not, I am not a in situ resource, I'm not a miner, I'm a spacecraft builder. But this mission, but I've thought a lot about sending humans into space. And for me, the key is two things. If you're going to manage, if you're going to keep humans, if you're going to extend human civilization beyond the surface of the Earth, you're going to need two things. You're going to need commercially sustainable enterprises, and you're going to need to be able to live off the land. And if you think about how, I'm sure Australia was colonized, and how America was colonized, and how we expanded out to fill and utilize the space of our respective countries, that's what it took. It took entrepreneurs, people willing to take risks in making businesses successful, and then people who are willing to live and struggle to sustain themselves, often in a very, very hostile environment. So that's what we're starting the process of today. We're starting that commercial process. How do we develop businesses that can actually make money in space? The big driver, the big challenge for space missions today is the cost of launching mass off the surface. The rockets that it takes to lift spacecraft and payload off the surface are very expensive. And we would really, if we could reload our spacecraft with propellant that is already out in space, we could launch much more efficient vehicles and really come up with a much more cost-effective business case. There's a lot of asteroids out there. There's a lot of them. The challenge is finding them and then having them in a place where you can use them. The reason I showed you that, the option A, the bag capture option, is that in my mind, one of the best business strategies would be is to find an asteroid like that, find a C-type asteroid that was hybrid, or even find a dead comet where you know there's water there, liquid water, frozen water, and then capture that and put it in an accessible place. Maybe it's around the moon, maybe it's somewhere else. Wherever it is, electric propulsion will play a big role in either getting to that or bringing resources back from it. Now, what are the usable resources? That's a big part of what the Offer of Mining Conference is talking about. The obvious stuff is water, which you can make propellant from, oxygen itself, which is a consumable that you need for humans in space. There are minerals, there are particularly valuable minerals. There's other things, and there's materials that you can build things with. All of those are things that are available in asteroids. Different asteroids have different types of materials. So we're just now starting that process. And ARM is really central to that. ARM will bring not only materials, but it will demonstrate core technologies. So it's a fundamental building block, I believe, in the future of meeting these commercial and eventually colonization of places off the Earth. So this chart kind of captures some of the elements that ARM is associated with, and I've already talked. I've talked a lot about that vertical path where the commercial and planetary defense applies. But it also, electric propulsion and the ARM capabilities could also be applied to planetary exploration. One of our next missions to Mars may use electric propulsion to deliver the payload to Mars orbit. And we've looked at other missions that can deliver large payloads to further out to deep space like Jupiter, Saturn, and beyond. And of course, we've also talked a lot about Mars and the moons of Mars. And again, we can deliver payload and systems to those places. But I was asked by a key congressman, what else can you do with this system? He wanted to go to a star. He would like to go to Alpha Centauri. Well, our electric propulsion system for ARM is a tiny step in that direction. Because that's what you're going to need, really, really efficient propulsion to get up to a fraction of the speed of light, which is where you're going to need to go to get out to the stars. And eventually, that's how we're going to do it, and we're a small step in that direction. Here's another interesting picture. This is showing a concept that we developed in which you take both electric propulsion and chemical propulsion and use them together. Use the best of both of them. This is a case where we're actually carrying a crewed habitat with humans aboard into the Mars system. Again, this is a rather futuristic image, but if you've seen the movie Martian, or do see the movie Martian soon, please look forward to it. I'm sure you'll love it. It's electric propulsion powered. So I'm going to close with this chart, just hitting some of the highlights of the ARM mission, things that you've already seen. I think you've got a good picture of what we're trying to do with this mission. I'd like to open it up for questions. Thank you very much.
Should be a couple of guys with microphones. So
if we can bring up the house lights so we can see your smiling faces, inquisitive looks, puzzled.
wow.
Okay, here we go. Gentleman over here.
How do you maintain focus and motivation for such long-term missions?
Good question. Well, that's a challenge of leadership. I think part of the nature of what we do, when we enter into the development of these missions, we know it's going to take years to do it. There's tons of problems to solve, and that's what engineers love, solving problems. So when I put together a team for the ARM mission, or the team I put together for Mars Pathfinder or Deep Impact, I was looking for people who shared my excitement, my enthusiasm, my curiosity, and had a lot of energy. They were driven. A lot of times the younger group, it was a younger group that worked with me on Mars Pathfinder. I love hiring people that are just, you can see their excitement in their eyes when they talk about it. I just hired a new systems engineer who said, this is my dream job. So when you get people like that, then my job as a leader is to cut through the red tape and help them be successful in what they want to do. So there's a lot of problems that we encounter, and one of the things I also like to do is share the stories of teams that have had problems and succeeded, that work through their problems and share those with the guys that are having big problems now. So engineering is a team sport. When you're doing spacecraft development, you take advantage of that. You build a sense of team and a sense of spirit. And that's what keeps us going through the ups and downs to the launch pad. And once we're there, the excitement of the launch, of course, all of a sudden we take a big breath, and then we realize, oh, crap, this isn't over yet. We've got another 5 years to go make this work. So it just takes a very special breed of people to do this. But I'm very happy to work with an organization that grows those kind of people. And we just live and breathe this stuff. Oh, I heard there's a tough questioner in the audience.
Will you be here on Tuesday?
What happens with the machine which captures the
Boulders?
Yeah, the boulder. When the humans go to Earth and they have everything they need from.
When the humans leave?
Yes, and the machine stays in space. What does happen to it?
Okay, an excellent question. I get that question from Washington, D.C. all the time. The answer is we will put it in a stable orbit. We will put it in an orbit around the moon in which the gravitational forces of the moon and the Earth and the sun find a very, very stable orbit. So even if the spacecraft stops working, or even if we could separate the asteroid away and leave it there, it will be stable, some of our analysis shows, for like 30,000 years. So it's a very good place to leave the asteroid. On the other hand, we could do with it what we did with the Grail spacecraft, which were to actually target them into the surface of the moon. And we could learn something from that. So we've got a lot of options to deal with the boulder. But one thing I can tell you, maybe it's what you were worried about, is that the asteroid is not going to come back and enter the Earth's atmosphere. We'll make sure of that. Okay, thank you. Next question.
Hi, my question is if more of these kind of missions and it becomes like commercialized, what is the problem with dealing with that space junk that's just left there? Because like, as you said, like maybe after we finish, we've tested, they're all brought home, the astronauts have come home and everything, and it's just orbiting around the moon for 30,000 years. I mean, like, that's just another piece of space debris that now is in the way. If you continually do that with all these other asteroids and spacecraft, just not in like asteroid missions, we end up with like the moon has its own ring system of space debris. Like, yeah, that's right.
Well, there are laws, international laws now, that are preventing us from continuing to generate debris around Earth orbit. We will probably have to develop similar rules around the moon system. But again, we have options with this machine. We can crash it into the moon if we like. That's what we did with the Galileo spacecraft and Jupiter. That's what we will do with the Cassini spacecraft and Saturn. But one of the nice things about our electric propulsion system is it's reusable. It can be refueled. And so we have the capability to extend our mission and go out and do other missions. But we will not be littering the orbit of the moon like we've littered the orbit of the Earth. I can assure you of that.
I have two questions. One is organisational, and it relates to the role of JPL with deep space missions versus the manned mission element in this, which I believe is another group in NASA.
Mm-hmm.
And my second question, I've forgotten. Oh, sorry, no, it relates to the SLS. And if you could just touch on the differences between the SLS and what 50 or 45 years of technological development may do to make that vehicle different from the Saturn V.
Okay. So I'm not sure, your first question was, what are the two organizations, JPL versus, say, Johnson Space Center? Well, JPL is the NASA center with primary responsibility for deep space exploration. And so most of the missions that have left Earth orbit, left the solar system, JPL has led. The human program is managed out of the Johnson Space Center in Houston, Texas. I spent 3 years down there as the chief architect for Constellation. Very different, those are two very different cultures. And part of what the ARM mission is trying to do is actually, and part of why I was asked to lead ARM, is that I understand both cultures. And we're trying to take something and learn something from those two cultures to try to change how we do human exploration. Human exploration is extremely expensive. And part of, in the ARM machine, the robotic machine, is what we call crew safe. It's not human rated. Human rated machines are very expensive. Crew safe is something else. And if we can continue to think along those lines to innovate about how we do the mission, we can maybe bring down the cost of human exploration. The SLS is at this stage is a really sophisticated new machine, but it's built on technology that has been in development. Actually, it goes back to the shuttle. The 4 engines that the SLS will use as it launches, 5 engines, I'm sorry, are actually shuttle main engines. They are the SSME engines, and those are the most advanced hydrogen-oxygen engines, most sophisticated, most perfect engines that have ever been built. But we're using used engines, not used engines, but engines that have already been built. That's keeping the cost down. We're strapping on very large solid rocket boosters, a 5-segment versus the shuttle 4-segment. So we're building on the shuttle heritage. And the central core of this thing is a huge 8-meter liquid hydrogen oxygen core with a sophisticated hydrogen oxygen upper stage. So we're pulling out all the stops on chemical propulsion. And it's in development now. We just passed the critical design review. We'll be ready to launch this thing in 2018, we hope.
G'day. I was just wondering how bipartisan is the current direction that JPL and NASA have currently? Because I believe that the last change of the executive changed from moon-orientated to Mars-orientated. So based upon the last guy's question, I was like, oh, how good is it to be very focused on a 20-year mission? How confident are you right now that the next change of the executive is going to stay that focused?
Are you with the media?
No, I'm just some guy, I'm a groupie.
I love those questions about Washington.
Sorry.
That's cool. It's been interesting because when we first rolled out this mission, NASA made a decision to align it with a presidential space policy, and that was not popular with the Congress, and we've been fighting that ever since. And the message that we should have been communicating then, and which we have been communicating now, is that ARM is central to the human exploration program, which does have broad support within the Congress. So we're getting more traction, more support, we believe. The proof is in the appropriations. When the Congress passes a budget, which it looks like they will this year, that will be the first indication that there's enough support for ARM from the key congressmen and the key appropriations committees on the House and Senate side. But it's necessary but not sufficient. Next step is that the president's budget has to come out. That has to show ARM as a line item, and then we need the next round of support from the Congress. So it's an uphill fight. It is definitely an uphill fight. Our science missions don't have this problem. That's most of the missions I've worked on are space science missions, and they enjoy the benefit of having a planning process. We call it the decadal process. Every 10 years, our planetary program, our Earth science program, our astrophysics program goes through this self-examination in which we identify the major missions we want to go do. And there's a certain funding line that the Congress has agreed to. And so we work within that. And so periodically we're able to, we mount the next Mars mission, we mount the next deep space science mission to Jupiter or Saturn or beyond. So the human program doesn't have that. We've looked for that. We'd love to have that, but we don't have the benefit of that. So we live through this process, which is pretty painful. Oh, there he is. Thank you.
This question is regarding all those uncertainties you had with regards to the boulder collection.
Yeah.
What are some of the arguments against all these uncertainties?
Well, my problem is there aren't any arguments against them. The problem is to try to quantify them as best we can and then develop designs that are robust to those uncertainties. And that's the nature of the kind of engineering problems that I'm used to solving. When we first developed the Pathfinder system to land on the surface of Mars, we were asked to land on the surface of Mars for less than the cost of the movie Titanic. And we invented this airbag system. And the airbag system, we believed, was robust against the uncertainties of the terrain of Mars. And it was. We proved it out. We've used it multiple times. So that's what you look for. How do I make this system robust against the uncertainties of the asteroid itself? The strength of the surface, the strength of the boulder, how well is it adhered? All of those are things that we will design and test, build into our system. But like I said earlier, we won't know until we get there. And so we need to have the capability, if we fail the first time, if for some reason the terrain is too soft or the boulder is too attached, we can go to another target. And that's our strategy. And it's going to have to be done very efficiently and very autonomously. Sir?
Yeah. On the same topic, let's say the boulder is not firm enough to be held, then you have the plan B to change and try to find another boulder. But let's say none of the boulders that I tried, they are firm enough. There is a backup option to collect debris or small fragments, just to come back with some material that can be analyzed. Thank you.
Yeah, there is. I mean, that's an option we have, is to actually capture, grab material as we land, or with a sampling device that are on the landing legs. That's not really, that's part of our option space. But I just want to point out though, there's one, as we look at our success criteria, one of our key sponsors is really most concerned about the electric propulsion system and getting it back. So our mission would be successful if we only bring back a little bit of asteroid material, as long as we get the machine back. And so part of our job during operations is to make sure that happens. So we've got to be very careful. And again, we'll be working it as we go. We'll be spending a lot of time characterizing the surface. We may bring along additional instrumentation that'll help us understand the nature of the surface better and tell the engineers and the scientists, here's what to expect. And then we have to build in to the system the ability to respond to those uncertainties in real time. And the nice thing, one of the nice things about going to an asteroid is it's a microgravity body. When you go to Mars, the gravity of Mars and the atmosphere of Mars is such that it's a real problem to get to land safely on Mars. To land safely on an asteroid is not a hard thing, but to operate on the surface is a challenge. And we're going to have to figure out, when we get there, how to deal with that. Now, there's two other missions that are going ahead of us. There's an Osiris-Rex mission, and then there's a Japanese mission, Hayabusa 2. They're going to two other C-type asteroids. Now, both, in the case of the Osiris-Rex, it's a touch and go. It's not going to spend any real time on the surface. I don't know a lot about Hayabusa 2, but I believe it's going to be landed. So we're going to learn more about the surface, just like we did with the Apollo program. JPL actually built the surveyors that went to the moon before the astronauts went, to understand the nature of the surface. One of the things we were worried about in Apollo was maybe the moon is covered with this thick layer of very fine dust. You step into it, you're going to sink. Well, we found out that that wasn't the case. But that's because we sent neat missions ahead of us. So it's a real problem.
Okay. Thanks very much for that wonderful talk, by the way. I'm over here, by the way.
Thank you,
That was
sir.
really inspiring, and it's great to hear that NASA's back in the human exploration business. My question is about the first stage, getting into orbit. Is there anything on the horizon to replace the chemical propulsion system? Is there anything, like I've heard of space elevators and space ramps? Must be something at the drawing board.
Nothing that I'm aware of that can launch the kind of mass we're talking about. That's why it's really a game changer to go to the Space Launch System. I mean, we can keep launching on smaller vehicles, but what you end up having to do is launch multiple rockets, rendezvous in Earth orbit, bolt them together, and take off from there. When you see in the movie The Martian this incredible giant Hermes spacecraft, well, that was not launched one time. It was actually built up, probably by an industry somewhere in cislunar space. And maybe they had been mining materials and building the pieces, on the moon or somewhere else. That's the kind of technology we're going to have to get to. I was once asked, what was my favorite part of the first Star Wars movie? Well, for me, it was the opening scene where you see this giant galactic-class battle cruiser. And I was thinking, what society had the resources to build something that big? That was really impressive to me. Today, we're just getting started in that direction, but we've got to get off the surface of the Earth and stop launching stuff out of this gravity well before we get to that point.
Maybe the last two questions.
I was wondering if you could go into a bit more detail into why carbonaceous chondrites were chosen. I imagine it's for water, oxygen, but also the potential to, fuel spacecraft and part of the debris around the Earth.
Yeah, the carbonaceous chondrites are my understanding of them, these are asteroids that formed in the outer part of the asteroid belt. They formed under cooler conditions. The composition has carbon, organic, possibly organics, and has hydrated minerals. Now, in some cases, there might even be water in some of them. We don't know. We've never really seen one up close and personal. We've seen only a few meteorites that have been carbonaceous in nature, because most of them will just burn up in the atmosphere. So the C-type, hydrated, has the potential to provide us water, oxygen. Maybe there's something else useful there. Knowing the ingenuity of the human species, if there's something way to make money, we'll find it. But right now, from my point of view, the best business case is hydrogen and oxygen. But it's got to be in the right location. If you've got to spend a lot of time going out to the asteroid, to the source, and then a lot of money and whatnot getting back from there, that's not going to be very efficient. I think of the electric car, I think of the Tesla. My chief engineer on the electric propulsion system is a Tesla. Of course he does. He's an EP guy. But when he wants to fly from LA or drive from LA to San Francisco, he's got to make sure the recharging stations are there. And he's tested them out. He's a smart guy. He's checked it out. But that's what it takes. You need the stations along the way. And I think that's where we're going with eventually the kind of work that ARM has just done the first step of.
Hi, I have two questions, if you don't mind. First question, with regards to 3D printing. I think in one of your slides you mentioned something about looking for... Yeah, right.
Oh, there it is. Thank you. Okay, appreciate it.
In one of the slides, I think you mentioned something about looking for material for 3D printing. Just exactly what type of material are we actually looking for? And secondly, I think the other day I saw a video on ISS that actually print a pizza on board.
ISS print a pizza?
I don't know. Something about printing a pizza in space. I can't remember exactly. But it's that's JPL interested in actually taking advantage of the CO2 environment to actually improve on the 3D printing technology that we have so far.
I think 3D printing has a lot of potential. We call it additive manufacturing. There's a lot of potential there. I've seen some amazing stuff built, just basically created. I saw a automobile valve, which is a very unique thing. It has to live in the very hot environment of an internal combustion engine, and it has to have a lot of strength and lifetime. And it's generally made out of two materials that are welded together. Well, what was done in this 3D additive manufacturing system was actually grow this valve out of the right materials transitioning smoothly, into this, useful product. So I think the additive manufacturing is an enormous capability. There's a lot of problems that can be solved, and I think we're just beginning to be able to do that. So I don't know where in the asteroid mining business that might be valuable, but someday we may be building a lot of things that way. For example, one of the problems that kept me up at night when I was working in human spaceflight was how do you keep humans alive for a 9-month mission to Mars, maybe 500 days on the surface and 9 months back. And you've got to have a life support system that's really robust. And you can't bring along enough spare parts like we do with space station today. So you've got to have a design that's, again, very robust to start with. But you ought to have the capability to fix things. And manufacturing in space, which is where we're starting to go, is the way to do that. If I have a valve or I have a motor or something that is failing, if I can manufacture that in space, I've got my spare part there. And all I need is my 3D manufacturing capability and the materials. So I don't know what materials are going to be the right answer, but I think someday that may be one of the values of the material that we have available in space. We don't have to launch the raw stock. We can have it right there in space.
Well, I think that brings us to the end. I've been a very entertaining evening. Please join with me in thanking Brian for this wonderful presentation.
Better be Australian, not Californian. Ah, very nice. Thank you. Oh, this looks wonderful.
And thank you all for coming along.
Thank you very much.